Well, I have 12:40, so let's go ahead and get started. Apologies for the late notice on not having class today. Like I said, I've had several people that have just been really stressed out this week. And so I was giving all my classes kind of a day away from class to kind of regroup and do things at their own pace here over the next couple of days. I will have these notes up pretty shortly after class ends today for y'all to look at. And Friday, I'll also have some notes for you. Friday, my wife and I have to go out of town for a medical procedure. It's nothing too worrisome or anything like that, but that's why I will not be available on Friday, but should be back on Monday, ready to go. We left off last time talking about rings, and the definition of a ring that we gave toward the end of class was that a ring is an abelian group under addition that has an associative multiplication and also has left and right distribution. So that was our definition of a ring from class last time. I wanted to go over some of the properties of rings today, give you some examples to kind of make it a little bit more concrete what a ring is, and talk about some of the pitfalls that students often make when working with rings. The first thing I want to talk about, though, is some of the rules of multiplication in a ring. Since we've already talked about all of the additive operations because rings form a group under addition, I didn't list any of the additive properties because they're just identical to what they were for groups. But you might be uncomfortable thinking that all of the normal multiplication laws follow through for a ring, just like they do on the integers. And for the most part, they are identical. If you multiply things in the integers in a certain way, then in a ring, you multiply them in the same way. You got to be careful about commutativity, and you got to be careful about cancellation, which we'll talk about in a second. But all of these properties that we know and enjoy about rings also, or that we know and enjoy about the integers, also carry over to rings. However, you can't just assume that they're true, right? You have to use properties of the ring to prove them. So I wanted to show you that real quick in a couple of proofs, just so you can get in the habit of using properties of rings to prove other properties of rings. So we'll start here with this very first one. A times 0 is 0 times A, which is 0. Seems fairly obvious. It's not as obvious as it seems. Here's a small proof of this. So if I wanted to prove this result, what you might think to do is say, okay, if I take 0 plus A times 0, we know from addition, 0 is the additive identity. So this is just A times 0. But I can think of 0 as being 0 plus 0. And by fitting in this 0 plus 0 term, I'm now allowed to use the distributive property of a ring to say that this is A times 0 plus A times 0. And what you notice here is that if you compare this with what we started with, the implication here is that 0 must be A times 0, which gives us the proof of what we needed here. So you can't just assume that A times 0 is 0 because that's the way it works in the integers. You have to do a proof using properties of rings to get that result. Similarly, I might look at this second one and say A times negative B. Well, I'm going to do something very similar to the first proof that we just did. I'm going to say, okay, A times negative B plus A times B is A times negative B plus B using the distributive law for a ring. But negative B plus B, because it forms a group under addition, negative B plus B is 0. And we just proved A times 0 is 0. So what you have here is you have an element plus another element gives 0. So that means that the additive inverse of A negative B is AB. Or another way to say that is that A negative B is the additive inverse of AB, which is what we were trying to prove in number 2. And the rest of these results are proved in similar ways. So this is the additive inverse. Finally, the last one that I wanted to look at with you here is the negation of the negation. It's not one of the properties listed, but it's one of the ones that you might think to prove. And that is, if you look at the negation of A, right, you would expect that to be equal to A. Well, here's a small proof of that. If you think of the equation negative a plus x equals 0, we know that that says that x is equal to a. But another way of saying that is that negative a, the inverse of negative a is a in the ring. So that's how we get the multiplication fact that -1 times negative a is positive a. It actually comes from the additive properties of the group rather than the multiplicative properties of the group. So that just gives you kind of a little highlight there of how we use these properties, properties of the ring to prove multiplication in the ring, similar to how it works for the integers, but you can't just rely on what you know about the integers because there's going to be some things that are different here. Okay, so one thing I want to talk about real quick is if you have an identity or an inverse in a ring, they are unique. There's no such thing as a ring that has two multiplicative identities or two inverses. And it's actually pretty easy to prove that, especially for the identity. So let's do a quick sketch of a proof here. If R has identity, multiplicative identity 1R, then suppose that 1R prime is another identity. Then you can say that 1R is equal to 1R times 1R prime. But since 1R prime is assumed to be another identity, 1R times 1R prime is 1R prime. So if you have two identities, you really just have one because the two identities would be equal to each other. The other result, so this is, you have unique identities. To see that you have unique inverses, consider that you have two elements. So suppose that a times x is the identity for R and x times b is the identity for R. So this one's a left inverse and this one's a right inverse. I want to show that A has to be equal to B. Then what you have is A is equal to A times 1R, which is equal to A times, so A is equal to A times the identity, but I can replace the identity, this 1R, with X times B. But that's the same thing as AX times B, and we know AX is also the identity. So you get that A is B. So if you have an identity in a ring, or if you have an inverse in a ring, they are unique. And we shouldn't be concerned about saying this is the identity or the inverse of an element in a ring. And of course, when I'm talking about this, I'm talking about multiplicative inverses. We've already covered all of this for additive inverses because the ring forms a group under addition, but not under multiplication, which is why we're checking a lot of the little multiplication facts. All right. So there are three very common mistakes that students make in assuming that multiplication in a ring behaves just like multiplication in the integers. The first mistake is what's called multiplicative cancellation. That is, if AB equals AC in a group, if it were a group under multiplication, we know it has cancellation. But in a ring, you cannot conclude that B equals C. And the reason for that is the ring doesn't have to have an identity, right? So since the ring doesn't have to have a multiplicative identity, then you might say something like, well, in the previous proof where I was trying to show that if you had unique inverses, I couldn't do this on the previous one, right? So I couldn't say, suppose A times B is 1R, but that's also equal to A times some other element B prime. I couldn't conclude, so I cannot conclude that B is equal to B prime. So this is what you might have thought to have tried. The reason I bring this up is when we were looking here at unique inverses, you might have thought, well, just suppose there are two elements, A times B and A times B prime, that give 1R, conclude that B equals B prime, and show that the inverse is the same, right? So show that B and B prime are both inverses of A, but they're equal to each other. While we were able to prove that the inverses are unique in a ring, you could not have proved it this way because you would have been assuming cancellation, and cancellation is only a valid property if you have a multiplicative identity, which a ring doesn't necessarily have a multiplicative identity. So if you're in a ring with identity, then you do have the cancellation law. But if your ring does not have identity, you do not have multiplicative cancellation, because you don't know that the inverse of the element exists, right? So if you want to tell me that if you want to cancel A on both sides, you'd have to multiply by A inverse on both sides. And we don't know that A inverse exists, and it won't exist if you don't have an identity. So you've got to be really careful about cancellation rules in a ring. The second mistake that I see students make is assuming that they have an identity. So for example, if we were in the integers and I told you that A squared was equal to A and asked you to solve that, you would tell me the solutions for that are 1 and 0. But if I don't have a multiplicative element 1 in my ring, then the only solution in the ring would be 0 to that equation. So you need to be really careful in assuming that there's an identity in a ring. Oftentimes there is not. And it turns out that mistake 1 and mistake 3 are linked. So this is a new definition for us, a zero divisor. A is a zero divisor in the ring R if there exists an element B in R where B is not 0, such that A times B is 0. So a zero divisor is any element of the ring that multiplies by a non-zero element and still gives you 0. Because typically when we think about the product of two integers being 0, we know that one of the two integers has to be 0. But in a ring, that does not necessarily have to be the case. You can have two non-zero integers give 0 without either of them being 0. A good example of this would be to consider the ring 0, 2, 4 in Z6. Is that the one I want? Yes. No, consider the ring 0, 2 in Z4. No, I can't do that either. Here's one. Consider 0, 3 I'm blanking on an example, but there are examples out there. We're going to look at one here in a second, so I don't want to spoil that one. But the point is, you can have two non-zero elements such that when you multiply them, you get 0. And if that happens, they're called zero divisors in the ring. I want to show you that having a zero divisor is equivalent to having the cancellation law. So if you don't have any zero divisors, then you have the cancellation law. And I want to show you that. So suppose that A times B equals A times C implies that B equals C. Then if AB is equal to 0, where B does not equal 0, then this says what? It says that AB, or 0, is equal to AB, which is equal to AC, right? But that implies that B would have to be 0. So R has no 0 divisors. Because if you suppose you have a 0 divisor, right? So if you suppose you have a 0 divisor, then this is the same thing, A times 0, which we know is 0. I kind of goofed that up. It should be, I know 0 is A times 0, right? But I also know 0 is A times B. So this would say A times 0 equals A times B, which doesn't equal AC. Sorry, I don't know why I put that in there. That implies by cancellation, if you have the cancellation law, that would imply that B equals 0. So if you think you have a 0 divisor and you have cancellation, then you really don't have any 0 divisors because B would have to be 0 by cancellation. So you wouldn't have a 0 divisor. So it turns out that multiplicative cancellation and 0 divisors are linked. We're going to have a lot more to say about 0 divisors coming up in Friday's lecture because they are integral to something we call an integral domain. So we'll talk much more about those on Friday. All right, let's look at several examples of rings, several common examples to start with. And then as we go through this, we'll look at some uncommon examples. And what I want to do is, as we go through these, I want to track and make sure we understand what is the identity of each ring. And I'm talking about the multiplicative identity. And I want to say, is the ring commutative? So does it have a commutative multiplication? I want to think about, does the ring have any 0 divisors? And then I want to ask the question, are all of the elements in the ring units? So remember, a unit is any element that has an inverse in the ring. So what I'm asking here is, are all the elements, do they all have multiplicative inverses? Do any of them have 0 divisors, etc.? So let's start with the real numbers. So if we start with R, the identity element for the reals is 1. It is commutative, and there are no 0 divisors. In the real numbers, the only way to get a product of two things to be 0 is for one of the two things to be 0. In the reals, does every element have a multiplicative inverse? The answer is yes. So the real numbers are a commutative ring with identity. Okay, what about the rationals? Well, the identity is 1 because 1 is a rational number. It is commutative because multiplication on the rationals is commutative. There are no 0 divisors, and every element has an inverse. If you take the element A, its inverse is 1 over A, which is in Q. So no problem there. We have, all the elements have inverses. What happens if we take the integers? Now here's where we're going to get our first kind of change. With the integers, 1 is still the identity. It is still commutative. There are no 0 divisors. However, not every element has a unit. In fact, the only element that is a unit is the identity itself. So not all of the elements are units. And case in point, if A is in Z, A inverse is 1 over A, but 1 over A is not an element of Z unless A is 1. So we don't have multiplicative inverses for all of the elements in Z. Another really interesting group here is the set of even integers. This is kind of a boldface E. If I talk about the set of even integers, they actually do form a ring. The way you can think of that is, if you add 2 even integers, you get an even integer. If you multiply 2 even integers, you get an even integer. You can check all the additive group properties. It has them. This is the same thing as 2Z, which we know is an additive group from earlier in the course. It has the distributive law because integer multiplication has the distributive law. It's also associative. So this forms a ring under our ring properties. Except, what is the identity of this ring? Because you skipped over 0, or excuse me, because you skipped over 1 because 1 is odd, there is nothing that acts like 1 in this ring. So it doesn't have an identity, but it's still a ring. It is commutative. There are no 0 divisors, and not every element has a unit for the same reason that not every element in Z is a unit. So this is a really good example here of a commutative ring with no identity. What about Zn? So the integers mod n. Well, 1 is definitely going to be the identity there. And at some point, we'll have a ring example where 1 is not the identity. 1 is typically our identity, but we're going to look at an example coming up where 1 doesn't have to be the identity. Is it commutative? Well, yes, we know modular multiplication is commutative. Are there any 0 divisors? The answer is absolutely yes, there are 0 divisors. You know, you can take, for example, Z4, right? In Z4, 2 times 2 is 4, which is equivalent to 0 mod 4. So there's an example where you have 2 non-zero elements that give 0. So there are 0 divisors in Zn. Does every element have an inverse? The answer there is definitely no. We've seen that earlier in the course when we looked at multiplication tables of Z for any composite N, because not every element will have an inverse in that case. You know, just take Z4 as an example again. What are you going to multiply by 2 to give you 1? It doesn't exist. There's no element that you can multiply by 2 to give you 1 mod 4 that exists in Zn. Okay, what if we're looking at a prime modulus though? So if you're looking at a prime modulus, the identity is still 1. It is still commutative, but turns out you don't get any 0 divisors in a prime modulus. And every element has an inverse. So prime modulus rings are very interesting rings to look at because they behave, if you go back up here and look, they behave like the real numbers. Z mod n, when n is composite, you might think that behaves like Z, but it doesn't because Z doesn't have any 0 divisors, but Z mod n does. So it's going to be a very interesting thing for us to track in the next couple of lectures. Multiples of Z. We've already seen 2Z here, but in general, multiples of Z where n is greater than 1. These guys don't have identities. And just like the even integers, they are commutative. They don't have any 0 divisors. And not all the elements are units. So it's just like the even integers I talked about here. Finally, we can look at direct products of rings, and those will turn out to be rings. We're going to say more about that in a later lecture. But if you look at something like Z plus Z, well, the identity, the multiplicative identity would be 1, 1. The operations there are commutative. There are no 0 divisors here, and there are no, not all the elements have units. So if you look at what this is most closely related to, Z cross Z or Z plus Z is closely related to the ring Z. They have similar profiles. So these are basic ring examples to kind of give you an idea of what the topic's about. What are the major things that we're considering? These are always the 4 things that we're considering in this module. Does the ring have identity? Is it commutative? Does it have 0 divisors? Are all the elements units? We're going to continue to ask those 4 questions over and over again in a variety of contexts. All right, so I want to give you some basic examples. I want to look at some of the properties of these different rings. The first one here is the set of all 2x2 matrices with real entries. We call that M2R. That's not to be confused, by the way, with GL2R. GL2R is the set of all 2x2 matrices with inverses. So it's the set of all matrices that are invertible that are 2x2, meaning that the determinants of these matrices are non-zero. In M2R, you can have matrices that don't have an inverse. They have determinant 0. But it turns out that they still form a ring under addition of matrices and multiplication of matrices. So if we look at the addition operation for M2, the addition operation is, taking A, B, C, D, add it to some matrix X, you can get 0, 0, 0 if X is the inverse matrix minus A, minus B, minus C, minus D. So that's easy enough. Addition is pretty easily explained. You add matrices component-wise. So the reason you get 0 here is A plus negative A is 0. B plus negative B is 0, and so on. So addition is pretty well defined here. We do have additive inverses. There's nothing really to worry about. Multiplication, on the other hand, is not really that easy here because we know matrix multiplication has the property that AB is not equal to B times A. So this thing is not going to be commutative. We know that the identity for multiplication is the identity matrix, which for a 2x2 would be 1, 0, 0, 1. And we know that matrices have inverses so long as this is the inverse of the matrix A. So if this is the matrix A here, A, B, C, D, then the inverse of that matrix is D, negative B, negative C, A. This is the 2x2 inverse formula that's given. And this inverse exists so long as this quantity down here, so long as that quantity does not equal 0. That quantity is the determinant. So this is the determinant of A. We need that to be non-zero in order for an inverse to exist, but that is not guaranteed to happen in M2R. So when it comes down to units, what I'll say is that we're not guaranteed. We're not guaranteed all A in M2R are units. There are going to be some matrices that don't have multiplicative inverses, some 2x2 matrices. What about zero divisors? Well, zero divisors can occur with matrix multiplication, and this is one of the more interesting zero divisor cases. Consider the following. If you take 4, 6, 2, 3, and you multiply it by -3, -9, 2, 6. And obviously this was constructed so that this would work out, but you get 4 times -3 is -12, plus 6 times 2 is 12. You get 0 in all 4 spots. So if you do typical matrix multiplication here, you will get 0. You'll get the 0 matrix, which is the 0 element, the additive identity element for M2R. So you can have 2 non-zero matrices that multiply together to give you 0. So you do have zero divisors. In case you're a little bit familiar with how matrix multiplication works, I know not all of you have had linear algebra. Let me kind of remind you of the way this works. If you take an A, B, C, and D, and you multiply it by a W, X, Y, and Z, then you get AW plus BY, AX plus BZ, CW plus DY, and CX plus DZ. So how does the situation here change if we're talking about M2, but rather than fill the matrix with elements from R, I fill them with even integers? Well, if you think back to what we talked about with even integers, the problem with even integers is there's not an identity element. So the main thing that happens with even integers is it goes from being a ring with identity that's not commutative to being all of a sudden just a plain old ring. So 1R doesn't exist. There's not an identity for that ring. So M2R is a ring with identity that's not commutative, but M2, where the entries are even integers, it's just a ring. It doesn't have an identity and it's not commutative. So it's just a plain old ring, just like the even integers were. All right. Here's a very interesting one that we're going to come back to often. This is called the ring of algebraic integers. The ring of algebraic integers is a set where you append one extra element to the integers. So Zi is called the Gaussian integers, or the ring of algebraic integers over I. And it's where you look at all things of the form a plus bi, where a and b come from Z. Now, you might think that that's just complex numbers, but it's really something more interesting than that, because in general, if you talk about Z add an element, then you're looking at all possible polynomials where the coefficients come from Z, and that element can be used as powers. So things like a plus b xc plus c xc squared, all of those are possible elements in this ring. So this would have polynomials of I from the complex plane and a from the integers, but it's basically all things that are of this form. Let me write down the other two real quick that I have here. What would the algebraic integers over square root 5 look like? What would be the set of all things that are of the form a plus b square root 5, such that a and b come from the integers? And, you know, just to show you that that group is closed, right? Because you might worry, well, is that going to be closed under multiplication? And it is, because if you take, like, say 2 plus square root 5 and you multiply it by 1 minus 3 square root 5, both of those elements belong to this set. If you foiled it out, you'd get 2 times 1 is 2, minus 3 times square root 5 squared, which is just 5. Then you would get plus square root 5 minus 6 square root 5. So this would be 2 minus 15 is negative 13. Minus 5 square root 5, that's an element that's back in that set. So we know we get something that belongs back to that set anytime you multiply two elements from there. You can check the other properties that you need, that this forms a group under addition, the multiplication is associative. All of those things are true. This forms a ring. And it means that we can look at polynomials where square root 5 is an allowable zero of that polynomial. It's something we could plug into a polynomial over the integers and potentially get an answer. The reason this becomes important is we know that there are some polynomials in the reals, for example, where if you try to factor them, your solutions are complex. So we can get complex roots by appending the element I to Z and forming this new ring. That's the purpose of these and what we'll be using them for. Similarly, if we wanted a number other than I, we could just append square root of, like, say, negative 5. So this is 5i, right? Or square root of 5i. So this would be the set of all a plus b square root 5, square root negative 5, where a and b come from Z. So it's an important example. We're going to say a ton more about these in the lectures that are coming up, but I at least wanted to get out ahead of that and show it to you. These are really important rings for us to look at. All right. Here's a really interesting example. It turns out that continuous functions on an interval form a ring. So this is going to be something for us to keep an eye on as we go ahead. So what this is saying is, suppose you have the set of all continuous functions that pass through the point 1, 0. Okay, so you've got the point 1, 0 here. And imagine every continuous function that passes through that point. I don't care what the functions look like. We call it f1, f2, f3, and so on. Take all continuous functions that pass through this point. Now, they have to be continuous on the entire real line, or they could be continuous on a closed interval containing the point 1, 0, and this is still valid. What does the operation look like on a ring like this? You know, so if you want to call this capital F is the set of all F mapping R to R such that F of 1 equals 0, right? That's the set that we're working with here. It's the set of all functions that take the reals and map them onto the reals such that F of 1 is equal to 0. And F is continuous. So that set is the set that we're looking at here. And what are the operations on that set? So if you take two functions, say f plus g, we define that to be the function f of x plus g of x. Okay, well, that's definitely going to be commutative. What about multiplication? So the function fg is f of x times g of x. These are both clearly commutative. So the operations that we have here are commutative. Do we feel like they form a ring? In other words, do we feel like we have multiplicative closure? Well, properties that you've learned learned in calculus are the sum of any two continuous functions is continuous, and the product of any two continuous functions is continuous. So we know that we have closure. Associativity is not difficult to prove. You could write that down and make that argument pretty easily. But I want you to be really careful here and think about identity. What is the multiplicative identity of F? So multiplicative identity would be, suppose F times G of X is equal to F of X for all X. Then that says that F times G equals F of X, which would imply that G of X is the constant function 1. But here's the problem with saying that G of X is the constant function 1. The way we've defined this set, all of the functions belonging to this set would have to pass through the point 1, 0, and the constant function 1 would pass through the point 1, 1. It would never pass through 1, 0. So this function is not an element of F, so F has no identity. We sort of cleverly defined what point all the functions would go through so that we could generate a ring that doesn't have identity. And if you think about it, you know, if a function passes through 1, 0 here, then both of these add to be 0. The 0 is really important. I couldn't do any arbitrary point. I couldn't say f of 1 equal to 5, for example, because then you would get, if you plugged in 1, you'd get 5 plus 5 is 10, and the sum of the two functions wouldn't pass through 5. 0 is really important here so that we maintain closure. So commutative and closure. So the choice of picking the point 1, 0 was not an arbitrary choice. It was chosen so that the ring wouldn't have identity, but still maintain closure. This is a really interesting example to think about. All right, new definition for us, a subring. So the generic definition of a subring is that it's a subset of a ring that is a ring itself with the operations of the larger ring that contains it. It's kind of a boring definition. It's exactly what you would expect. It's a subset of the ring that's a ring in its own right, using the operation of the larger ring. When we talked about subgroups, we gave a similar definition for a subgroup, right? It's a subset of a group that forms a group under the operation of the containing group. And we had what we called a subgroup test? Well, we also have a subring test. So the subring test is, rather than check all of the group axioms and check that multiplication is closed, multiplication is associative, and the distributive law holds, you'd have to check all of those things to prove that something's a subring. You really only have to show two things. The first thing that you show is, well, I guess three things. You show that the set is non-empty. Then you show it's closed under subtraction and multiplication. So if you have a candidate for a subring, all you have to think about is it closed under subtraction and multiplication? That's it. That's all you have to think about. Because if it's closed under subtraction, it's a subgroup. Think back to our subgroup test. And if it's closed under multiplication, then it's going to inherit the associativity from the other ring. So it's going to inherit it. Once it's closed, you know you're good. So closed under subtraction, closed under multiplication. I don't really want to go through the proof of this because it's exactly what I just kind of spilled off. There's a proof in the notes. It's not a difficult proof. Basically is once you have that something's non-empty, so let C be an element of the subring S, then you know if you have closure, C minus C, which is 0R, must be an element of S as soon as you have an element in there. So as soon as there's an element in there, if it's closed under subtraction, you get the additive identity. And once you have the additive identity, you get additive inverses. And once you get additive inverses, you get closure under addition. So you get all of the properties just from knowing that it's closed under subtraction, because subtraction of any element that exists can generate the zero element. There's more to the proof than that. I encourage you to look through it after this. So I want to do two quick subring examples with you. First is I want to go back to those Gaussian integers that we talked about before. Remember, the Gaussian integers are the set of all complex numbers such that A and B are integers. So if you were plotting the complex plane and you had grid lines spaced out by the integers, these would be all the points that lie on the intersections of the grid. Okay. I'll just start by saying this is clearly a subset of the complex numbers and is non-empty, since since 0 is clearly an element of this ring. So we know it's a non-empty subset of the complex numbers. So let's look at closure under subtraction. If you take an A plus BI and you subtract a C plus DI, well, by rules of complex operations, complex subtraction, this is A minus C plus B minus DI. And if A, B, C, and D are all integers, then A minus C is also an integer, and B minus D is also an integer. So this thing belongs to the Gaussian integers. Is it closed under multiplication? Well, if you take A plus BI times C plus DI, you can see that this is A times C plus BCI plus ADI plus BDI squared. Remember, I squared is -1. So you get AC minus BD plus AD plus BC I. This is an integer. This is an integer. So as a whole, this is an element of the Gaussian integers. So it's closed under multiplication. It's closed under subtraction. It's non-empty. So by the subring test, this is a subring of C. And you can still use the notation that we used for subgroups. You can still use this notation. From context, it's usually clear that you're talking about a ring rather than a group. So it's not very often that you get confused by using that symbology for subring. But there's not really another notation that we would want to use here. Okay, let's look at one more and we'll call it a day. This one's pretty interesting. I want to look at the ring Z6. So this is the set of integers 0, 1, 2, 3, 4, 5. But I have two operations. I have multiplication mod 6, so addition mod 6, and multiplication mod 6. So this thing is closed under both. It's pretty obvious that it's closed under both. I don't think there's really much to think about here. But because this is a composite modulus, if you look at the multiplication table for Z6, what you immediately notice is that there are some elements, like say 2 and 4, that don't have inverses because the element 1 doesn't show up anywhere on their row. And because of that, we don't really have a multiplicative inverse for some of these subrings, or well, we do, but it's going to be a little bit different. So let's think of it this way. What are all the possible subrings? Well, you should always start at the top, right? The ring itself, so is a subring of itself. Right? So the ring itself is always considered a subring. It's a pretty trivial example. And if you start at the bottom, if you just take the element 0, this is the trivial subring. So just like we had trivial subgroups, you have trivial subrings. If you just take the additive identity, that always forms a subring. And it's called the trivial subring. But what I'm interested in are the ones that lie in here, in between. So what we need to do is we need to look at this multiplication table, because the real limiting factor here is going to be closure under multiplication. You know it's closed under addition because it forms a group. So think about closure under multiplication. And if you look at the multiplication table, which elements are closed under multiplication? In other words, their row in the multiplication table is a closed row, and it doesn't eventually involve all of the elements. Well, if you look at 2 and 4, if you multiply 2 and 4 together, mod 6, you're only getting 2 and 4 back along with 0. So it looks to me like 0, 2, and 4 form a subring. And I'm going to draw a lattice of the subrings here. 0, 2, and 4 do indeed form a subring. The other one that's pretty obvious to look at is 0 and 3. 0 and 3 also forms a subring. So this is subring of order 2, subring of order 3. Now, what's interesting to talk about here is what is the identity, 1R, the multiplicative identity, for the subring 0, 2, 4. I want y'all to look at that and tell me, does 0, 2, 4 have an identity? What do y'all think?
Is it 4?
Is it 4? Well, let's look. 4 times 0 is 0. 4 times 2 is 8, but mod 6, that's 2. 4 times 4 is 16, but mod 6 is 4. So if you multiply 4 by another element of this ring, you get that same element back. So 4 turns out to be the identity for this subring. So I'm not willing to say yet that if the entire ring has an identity, then so too will its subrings. But that's something that you should be very aware of. If I looked at it for 0, 3, if you take 3 times 0, that's 0. If you take 3 times 3, that's also 0. Because you're, excuse me, that's also 3. because 3 times 3 is 9 and 9 mod 6 is 3. So it looks like over here that 3 is also the multiplicative identity in this subgroup or subring. So Z6 is a commutative ring with identity, and so too were both of its subrings. Both of its subrings have identity. But what I want you to understand here is the identity element for Z6 is 1. And the identity elements for the subrings do not have to be 1. They can be different elements, and you need to be very careful about that. We're going to see some other examples, especially with these composite modulus rings. We're going to see some other examples where this is the case. All right, so I feel like that's a good starter for us. That'll get us into Friday's topic. It should get you well into the homework as well. You can start looking at whether or not things are rings, whether or not they have units, whether or not they have zero divisors, and think about the subring test here. So that's all for today. We'll look at the next section after the ring section, which involves domains and fields on Friday. Y'all have a good day. Thanks for stopping by.